that end our discussion for today.
Genomic has
Another area
that makes plants easy targets.
Yeah. Greeting everyone. Welcome to our podcast, Applying Omics Technologies for Crop Improvement, a functional genomics and proteomics approach for sustainable agriculture and climate resilience. I'm Kelvin and I'm joined today by Shafika, Lydia, and Lorena. Today, we'll be discussing how advanced omic technologies are reshaping the agricultural sector and providing innovative strategies to address the industry's most urgent challenges. The reality is, agriculture is now at a pivotal point, with the global population on track to hit 10 billion by 2050. Food demand is accelerating rapidly. Meanwhile, farmers are dealing with escalating climate risks, tightening water supplies, persistent pest threats, and a reduction in usable farmland. Traditional agricultural practices simply aren't enough to close the gap. That's why industry leaders and researchers are leveraging omic technology, especially functional genomics and proteomics, to find new scalable solutions. Functional genomics allow us to analyze and interpret the genetic architecture of crops, pinpointing genes linked to increased yield, resilience, and nutritional value. In parallel, proteomic delivers critical insight at the protein level, showing us how plants actually respond to real-world stress factors. So, how are these technologies being implemented on the ground? What tangible outcomes are we starting to see? Well, Shafika, could you share how genomics is actively being used to implement performance and perhaps provide a concrete example from the field?
Absolutely, Calvin. Genomic has revolutionized how we approach crop improvement by allowing us to precisely identify and manipulate genes linked to important traits. For example, genome-wide association studies (GWAS) have helped scientists pinpoint genes related to seed size, growth rate, and photosynthetic efficiency. Using marker-assisted selection and genomic selection, breeders have developed high-yielding rice and maize varieties that are not only more productive but also more resilient to environmental pressures. Lydia, you might find this interesting. Genomic is also helping us breed crops that can withstand drought and salinity, two of the biggest threats of climate change. For instance, by introducing the DREB genes into wheat, researchers have significantly improved its drought tolerance. Similarly, targeting the SOS pathway genes in rice has led to varieties that can survive in salty soils.
That's impressive, but what about nutrition? Can genomics help address malnutrition or improve the quality of food?
Great questions. Genomics plays an absolutely critical role in biofortification, which is the process of enhancing the nutritional value of crops to address key health issues on a global scale. It's an innovative approach to combating malnutrition, especially in regions where variety of rice that has been genetically enhanced to produce vitamin E, also known as a beta-carotene. This nutrient is essential for preventing vitamin A deficiency, a condition that can cause blindness and increases susceptibility to infections, especially in children and pregnant women. Golden rice has been specifically developed for regions in Asia and Africa where rice is the staple food, making it an impactful solution tailored to the dietary habits of the population is designed to help. With the advancement of gene editing technologies such as CRI, SPR, Cas9, the field of biofortification has made leaps and bounds in recent years. Unlike traditional genetic modification methods, which often involve introducing foreign DNA, tools like CRI, SPR enable precise edits to a plant's existing genome. This allows scientists to enhance the crop's natural ability to produce vitamins, minerals, or other nutrients, while keeping its genetic makeup largely intact. This precision not only improves the nutritional profile of the crops but also addresses public and regulatory concerns surrounding genetically modified organisms, GMOs. By avoiding the addition of foreign DNA, these genes-edited crops are more likely to gain acceptance from consumers and regulators alike. But biofortification doesn't stop just at provitamin A or rice. Other successful projects include zinc-enriched wheat, iron-fortified beans, and cassava with higher levels of essential amino acids. These efforts are targeted at solving specific nutritional deficiencies such as anemia and stunted growth, which continue to affect millions of people worldwide.
And I like to briefly highlight another area where genomics they delivers real value, which is in disease and pest resistance. Through pinpointing resistant genes like NBS-LRR, researchers they have helped crops to such as wheat to stand up to disease like rust, and with innovations like berry cottons, we are seeing pest resistance crop that cut down on chemical pesticides use and booster sustainable agriculture. And now, shifting focus a bit, let's talk about Proteomic, which is my main area of expertise. And unlike Genomic, which outline a plant potentials genetically, Proteomic it give us snapshots of what actually happening inside the plant at any given moments or conditions, environments, and this is absolutely crucial for understanding how crops respond to environmental stressors, diseases, or climate change. You mentioned stress tolerance is exactly where Proteomic shines, and crops they have become under continual pressure to stress factors such as heat, salinity, or pathogens. And researchers they use proteome analysis to observe changes in the protein produced when the plant is exposed to various conditions. And for example, it has been reported before that in salt-tolerant rice, we can observe an uptick in the specific protein like dehydrins and heat shock proteins. And when the plant encounter drought, high temperature, or salinity, and these proteins It helps the crop to adapt and survive, which is vital for ensuring stable yields in challenging conditions and environments.
That's fascinating, Lydia. How does proteomics contribute to food quality or safety?
Absolutely. And Proteomic, they has become a pivotal player in elevating food quality and nutritional standards, and not just understanding about how plants protect themselves. And when we analyze the protein makeup in crops, we're not just gathering the data information just for the sake of it. It's like we actually opening the doors to developing a product with improved health benefits. And for instance, in maize, this approach it has allowed us to pinpoint precisely what set the high protein varieties apart, especially when it comes to key proteins like zinc. And let's take rice as another example. And by leveraging the proteomics, researchers they have managed to enhance the lysine contents, addressing a long-standing gap in staple grains, and that's tangible upgrades in nutritional value, which is increasingly important in today's market. On the safety fronts, Proteomic there is equally invaluable. Certain crops they are known to have naturally contain allergenic proteins that can affect an individuals, and Proteomic it gives us the tool to accurately identify the allergenic proteins like gluten in wheats or peanut allergens, and to detect the harmful toxins like mycotoxin resulting from fungal contaminations. This means when moving forward to towards a food supply that's not only more nutritious but also significantly safer to consume. And Lorena, with all of these advances, how do you see functional genomics and proteomics working together for a more sustainable future?
Thanks, Lydia. So here's the deal. The real value here comes from pulling these technologies together. Genomics lays out the roadmap, but proteomics, that's where you see which genes are actually stepping up and making things happen in real world conditions. When you merge these insights, you're not just guessing about better crops, you're actually developing varieties that deliver higher yields, improved nutrition, and way better resilience against stress and disease. Looking forward, the smart play is all about integrating multiple omics, genomics, proteomics, transcriptomics, metabolomics, the whole toolbox. This holistic approach lets us get a complete, actionable view of plant biology. The end game, the crops that are more efficient with resources, demand fewer chemical inputs, and support both productivity and sustainability. It's a win for business, for the environment, and for the food supply chain.
Oh, you did mention sustainability. How do omics technology help to reduce agriculture environmental footprint?
Okay, let's get straight to it. By strategically focusing on the specific genes and proteins responsible for stress management and disease resistance in crops, we can seriously reduce our reliance on fertilizers and pesticides. Technologies like CRISPR are already letting us disable genes that makes plants easy targets for pests, which means less need for chemical intervention. On the proteomic sides, we are learning to identify and leverage beneficial soil microbes, which naturally boost plant health and productivity, acting as organic fertilizers or even breaking down harmful substances in soils. It's a smarter and cleaner approach. So, to sum up, integrating functional genomics and proteomics is transforming agriculture. We are looking at the higher yields, reduced environmental impact, and a much stronger ability to adapt to climate changes. In today's market, that's a competitive edge you don't want to miss.
Well, with that end our discussion for today. Thank you everyone for this very insightful discussion. It's clear that Omic technologies are key to building a food secure and environmentally sustainable future. And thank you to our listeners for joining us on this journey into the future of agriculture.
Not yet, bro, not yet. Developing varieties that makes the
You're
Yeah, absolutely.